Good evening, everyone, and welcome to another installment of our Ig Nobel Talk series. Here at the American University of Beirut, AUB, we take a great pride in striking curiosity in the youth minds. And today's Ig Nobel Talk will be triggering, insightful, to say the least. On March 4th, 2019, we launched the 8th initiative of our Transformative Education Drive at AUB, in which we host Ig Nobel Prize winners for public talks. One of the core aims of our Transformative Education Drive is to spark potential in the younger minds. The Ig Nobel Prize, founded by Dr. Mark Abrahams, is bestowed every year to 10 individuals who make people laugh and then think. The winners receive their awards from Nobel Prize winners in Sanders Theater at Harvard University in front of a crowd of around 11,000 people to celebrate the unusual, honor the imaginative. These talks highly intrigue the interest in science and give a platform for Ig Nobel Prize winners to share their discoveries and inventions with the younger generation in hopes of setting an example. It is of vital importance that we keep on asking questions and feed our curiosity. Fascinating answers are only yielded by great minds who dare to question their surrounding reality. Today, we hope to not only extend your knowledge, but also make you profoundly excited in our one-of-a-kind talk. I am truly thrilled to host 2017 Physics Ig Nobel Laureate, Dr. Marc-Antoine Fardin, for today's Ig Nobel talk entitled, "Are Cats Liquids?" Dr. Fardin obtained his PhD from the University Paris Diderot and MIT on elastic flow instabilities in surfactant solutions. His research interest from ultrasound velocimetry of flow instabilities in simple and complex fluids to cell and tissue mechanics, pinching and coalescence of fluids, metabolism, and many other research areas. Since 2014, Dr. Fardin has been a permanent CNRS researcher at the Institute Jacques Monod. For the very diversified, esteemed audience, as it was the case with our previous Ig Nobel talk, we will particularly give the floor to the young minds to ask questions first. For the young people in the audience, please enter in the QA box your name, your age, your school grade, and which school do you go to. For the university students, kindly enter your name and major before asking the question. For everybody else, please enter your name and what do you do in life. Today, you will laugh, you will learn, and you will question multiple things which surround you. Without further ado, Dr. Fardin, the floor is all yours.
Thank you, Bilal. And everyone, everyone can hear me, means you can hear me. The other ones can't answer. So yes, thank you for the invitation. I'm very happy even to do this online. I hope I will make you laugh. I won't hear you laugh back, not as if I was there. So I'll be able to imagine that everything I say is hilarious. But yes, I also do hope to make you think on this kind of silly question, which is here on the title. So the question is, are cats liquid? And I did not come up with the question myself. I saw it online a few years ago. I mean, it was almost 10 years ago now. I saw it on a few websites, and they were asking these questions. And it made me think. It made me think about what I thought about what a liquid is and what science thinks today and has been thinking about what a liquid is. And so I think that the idea today is to bring you with me on this kind of quest to understand what a liquid is by using this silly question of are cats liquid? So are cats liquid? I mean, I'm really happy myself that I asked myself this kind of funny question, and I want to encourage you to ask similar silly questions, because eventually, I mean, it get you invited to give a talk at AUB, for instance. So it's good. So basically, like, what is a liquid? What is a solid? It's a very old question, and I want to kind of put it back into context. And it has interested scientists for a long time, and it has also inspired artists. So that's the reason why I put this painting here. It's a painting by an artist called Svetlana Petrova and her cat Zarathustra. And for those who know, it's really based on another painting by Salvador Dali, which is called The Persistence of Memory. And as you will see as the talk goes on, really the question when you try to understand what is a liquid, and so in particular if cats are liquid, is a question of time. So it's really what I want to get to, but it's going to take us a little bit of time to get there. But basically, the idea is to question what all categories like liquid, solid, and gas are. And it can seem a little strange, but like we're in the 21st century, and those old, very old words, they still kind of, trouble us and challenge us. And in the 21st century, I mean, if it's a little weird to imagine that those concepts can still elude us. And because we're used in the 21st century to like a man-made word. I mean, everything around us has a name, it has a category, everything is classified. So you have, everything is already ordered. But it wasn't always like this. I mean, before we could make the difference, sorry for the siren, before we could make the difference between toothpaste or a shampoo or a soap, we had to first try to figure out what was going on around us in the natural world. So a while back, but not that long ago, not everything was categorized, and we had to build those categories to kind of sort the various things that were around us and try to put them into various bags, I mean, into various classes. And it was very important. So here you see a cave painting from France. So I think it dates back a little bit more than 30,000 years ago. And back then, people spent a lot of time, I mean, spent great care painting the stuff that was surrounding them, and in particular, the various animals. And it's very clear when you see those paintings that they had a clear idea of the various classes of animals. So you see, for instance, here on the right, things that were actually mountain lions. I mean, they were European lions. So they were lions that were living in Spain, in France, in Lebanon. I mean, they were everywhere. And you had rhinoceros and all of that. And so it's very clear when you see those paintings that they knew how to classify the various animals. And it was very important to make the distinction between what they could eat and what could eat them. So basically, are cats liquid? So from the perspective of our ancestors, they already knew what cats were. So they already knew that some animals were kind of cats. So lions and, tigers or whatever, they were kind of part of the same family. But liquid, I mean, they were wondering what a liquid is, and we're still wondering what a liquid is today. So it's important to understand that it was very vital for them to have different categories and to really take great care in sorting out what's in this category and what's not. So imagine you're walking in the forest and you see like weird little things that have a foot and that have a hat. I'm talking about mushrooms. I think I looked it up. I think in Arabic it's fatran. So it's for us it's just a word. So if it's a word that we've learned when we're little, like in school, or our parents taught us what the word mean, And then every time we say the word, everyone that hears it like understand, and it has already the category in its mind. But for people before us, they had to really build those categories. They had to like carve what is a mushroom and what isn't. And it's this kind of category making, it's still going on. So people still today are specialists in mushrooms, and they say, oh, actually, this stuff that what people have called a mushroom for centuries, it's not really a mushroom. And for our ancestors, it was vital. I mean, it was because the thing is that some of them are very good to eat, others will kill you. And the thing is that you cannot just base your categories on the things, on the appearances. I mean, basically some stuff, some mushrooms look the same, but are very different in the sense that one is very good, the other one will kill you. And so it's very important to go beyond appearances and to really try to build categories, not just on how things look, but on how things behave and the effects that they might have. Because the thing is that some stuff look the same, but are very different. So for instance, on this image, what you're looking at is not a flower, it's a praying mantis. So it looks like a flower, but it's not. And so some things look the same, but are different. And some things look different, but are really the same. And so I give you here a few examples of this. So on this slide, what you're seeing is on the top left here, you have a spaghetti. And so you have a spaghetti and it's being pressed vertically. And at some point, it just shatters and breaks. And on the bottom right, you have like big metallic beams that are like the structure of some building. And so if you look at those two things, they are apparently very different. But if you study the fracture of spaghetti, and in particular, the fact that if you push on a spaghetti like this, it never breaks in only two pieces. The conclusion that you reach, I mean, the stuff that you discover when you kind of are interested by those spaghettis actually can be useful for the design of building. And so I took this example. One reason is that this example actually also got an Ig Nobel Prize. I think it was in 2006. So they showed that spaghettis never break in two parts, and they also showed how this could be useful for building design. Another example here is of a cup of coffee on one side and of a big, huge hurricane on the other. So if you look at those two things, I mean, they really look different. One was created by just twisting a spoon into the cup, and the other one is a meteorological phenomenon that just spans hundreds of kilometers. But actually, a lot of things, like a lot of insight, can be gained by considering those two things as part of a big, as part of the same big category, and that is the category of fluids. And so when people started thinking of gas, or clouds, which is the case for the hurricanes, on one side, and then on the other side, coffee, which is a form of liquid, when they started thinking about those different things, apparently different things together, they gain a lot of insight onto what causes the fact that sometimes you have those vortices or whirls, and more generally, when you really start steering, when the vortices are many and a lot of sizes, people talk about turbulence. So basically, it's another example of two things that are apparently completely different, but if you think about them in the same way or in similar ways, you can gain a lot of insights. And the liquid or water, if you want to take an example of a liquid on one side, and cats on the other, if you think of them in your mind as part of the same category by asking the question, are cats liquid? Similarly, you can gain some insights, not really on cats. I mean, we know them probably more than we know liquid in general. What you will gain insight on is really on what a liquid is and what you thought was a liquid and what a liquid is. I mean, basically what people think of a liquid now. So if you are interested not just in mushrooms or in the various animals that surround you, but if you're really interested in everything that surrounds you, if you want to try to understand and categorize, to try to name and kind of structure in various groups the different things, everything that surround you, small and large, what could you use as the basic categories? I mean, there are a lot of various systems of naming and classifying the world. Some of them have two categories, old ones are good and bad, the earth and the heavens, all of those are very old and very persistent classifications. And some have three categories, some have four. One that I want to talk to you about is the one that is depicted here. And it is the four categories called the four elements. It's a very old way of kind of um, describing the world. It was used in antiquity, and it's still used sometimes today in fictions and stuff like that. So I'm pretty sure you're familiar with it. And the idea that the people had, so it was basically like 2000, between 2000 3000 years ago, they were trying to categorize and classify the various objects that were surrounding them as based on mixtures of four indivisible fundamental elements. So there was earth, which is represented here. They had fire, they had water, and they had air. So for instance, they would say stuff like that. They would say, well, a cloud is not elementary, so it's a mixture of water and air, for instance. And they would say, well, if you look at the smoke that comes out of a fire, the smoke itself is also a mixture. It's a mixture of fire. Sure, it's hot. It's a mixture of air. It's buoyant, it goes up. And it's also a mixture of earth or dust, because when you look at the smoke, it creates those kind of small particles of dust. So they would say stuff like that. And basically, the four elements, it's a good example of whenever someone tried to, or some people try to categorize things around us, then automatically, I mean, it's very good to try to categorize, and I mean, it's inevitable, you have to just name stuff. But then it's also important to question the kind of categories that you first kind of write down, the first you first thought about. So then you have kind of this constant battle between two camps. So you start with the four elements, that's your starting idea, starting hypothesis. And then you have two kind of tendencies. One is to say, well, there are really more than four elements. There might be five or six. And the other tendency is to say, well, there might be less than four elements. So what I want to describe to you a little bit for the elements is where you can get by going one way or another, because we'll see that for answering the question, are cats liquid, we're basically going to be doing the same thing, but like in a slightly more modern way. So one very famous advocate of the more than four elements was the Greek philosopher Plato. So again, I think it was maybe 24 centuries ago, 24 centuries ago, so a while ago. It's this guy that wasn't a statue back then, but it was a real man. And he said, well, I like the four elements, but I think that there is a fifth one. And he said this for several reasons, and he called this the ether. One reason was religious. I mean, back then in Greek mythology, there was this idea that the gods really had this substance that was different from the one that you had on Earth. And so it was kind of, there were good religious reason to think that the ether was an additional element to the four traditional ones. But there was also another argument for Plato, which was kind of mathematical. So Plato, back then, he was fascinated. I mean, he was interested in a lot of topics, but he was fascinated by what is now called the Platonic Solid, but they are really also another name is the regular Polyhedra. So you certainly know a few of those. So for instance, the cube, which is here in blue rotating, or here. And the regular polyhedra, they are shapes in 3 dimensions where all the faces, all the edges, and all the vertices are the same. So if you look at it from different angles, it always looks the same from those different angles. And what Plato discovered, and I was kind of amazing to him and to everyone then and still now, is that there are only 5 regular 3-dimensional polyhedra. And so, you know, the cube, another one is the, how is it called? The tetrahedra. It's the one, it's kind of a pyramid made of 4 triangles. You have also like kind of this diamond shape here, which is called the, how is it called? Is it called the octahedron? And then you have the dodecahedron. I have an example at home. So it's 12 faces that are made of pentagons. And then you have the icosahedron here, which is 20 triangular faces. And so Plato's idea, he was fascinated in those 5 polyhedras. It was like, oh, this is great. And I know mathematically that this should be 5. And then there was this whole other like kind of physical or metaphysical theory of the elements. And so it was like, how can there be 5 kind of elements in mathematics and 4 in physics? So he said there are 5 elements in physics. You can see that it wasn't really a scientific point, but basically this philosophy, I mean, the idea that he has and the people that kind of thought in the same way had, was that you can kind of get an insight on the various physical elements, the various things that exist as elementary in the physical world based on their mathematical or microscopic structure. And that's something that is still very much alive today, this idea. So for instance, today we don't really talk anymore about 4 or 5 elements, we talk about chemical elements. And so in the 18th century, end of 18th century, during the American and French Revolution, you had people, very smart chemists, who did something amazing, which is that they came back to the idea that, I mean, they show basically that the ancient idea that air was a fundamental element could be proven wrong. And so by this, to do this, they took air, like, you know, just took a jar of air, and by various chemical transformation, they could see that actually air was made of like a mixture of different gas, and that those gas were more pure or elemental, if you want, than air itself. So for instance, they showed that first they showed that it was basically a mixture of oxygen and nitrogen. And it started a whole thing. I mean, basically people started breaking up various things that were surrounding them, solid or liquid or gas, and they realized that basically like a lot of the things could be understood as made by mixtures of various chemical elements. And so you know this table, it's still to this day like in pretty much all of the science classes. And it was basically this that was started by the discovery that air was not elementary. So this is still a very vivid part of science, which is describing what things are based on their chemical or macroscopic components. But you see that by saying, well, there might be more than 4 elements, then you go 5, and then like a few, like a little bit more, like a few centuries later, you've reached not 5, but like more than 100 elements. So then there is the other tendency, which is to say, well, there might be not 4 elements, but less than 4 elements. And so in this camp, like in this kind of less than 4 camp, there was a guy, I mean, one of their main champion also in ancient Greece was a guy named Heraclitus, which is on the other side here on the bottom left. And he kind of found like the best like rebuttal to people who thought that the world was made of several elements, 4 or 5. He didn't really care. He said everything is really made of one element, and this element is called fire. I mean, he chose fire. But really by fire, he meant like change. Basically, he said like, it's not that you have different things, different elements. You only have one thing, but then this thing can change over time. And so the appearance of what you have will change, but essentially the thing will still be there. So different kind of idea went on a different direction. But basically, his motto was that everything flows. That in Greek, it's a penta-rei, which means everything flows or everything changes. And it is this motto, penta-rei, which is also the motto of rheology. So rheology is the scientific field that I've been part of for a while, and I still work a lot in this field. And it was created about 100 years ago by physicists, chemists, and engineers as a way basically to study the intersection, I mean, to question what we meant by liquid, solid, and states of matter. And so rheology, it has the same roots as in penta-rei. Rei means to flow in Greek. And you find the same roots in a few other words. One you certainly know, but so one is diarrhea. So the rhea in diarrhea is the same as the rheo in rheology. It's a science here of flows. And another word is logorrhea, which is speaking constantly without necessarily meaning anything. So rheology is the study of deformation and flows and of kind of the fuzzy boundaries between liquid and solid and between liquid and gas in some sense. So the 4 elements that people studied in antiquity, they were progressively replaced during the Renaissance, and they're by the states of matter, what people call the states of matter. And usually people start with 3 states of matter, which is solid, liquid, and gas. And it, in the same way that the elements was really not the final word on anything, the states of matter are also not final or definitive, but they are used as a way to basically build like more precise description of the world. And here again, you have 2 kind of camps. You have people who say, well, there are really more than 3 states of matter, and there are people who are saying, well, there are really less. So first, what are they? How are they defined? So the standard definitions are these. So if you think and talk about a solid is defined as a material that will maintain its shape and volume. So if you put a little metallic bead in a glass of water, the metallic bead is not going to adopt the shape of the glass. It's just going to keep its shape. A liquid is a material that maintains its volume, but it will adapt its shape. So if I put water into a cup, the water takes the shape of the cup, but it keeps the same volume. And a gas, finally, is an object that will adapt its shape and volume. So if you blow up smoke inside a room, the smoke is going to disperse in the entire room as time goes by. So if you are, looking at those 3 states of matter and saying, well, as Plato did for the element, you say, well, there might be more than 3. One very common way of doing this is to say, well, there is liquid, there is solid, there is gas, but there is also another state, which is called plasma. And that describes, for instance, the materials that are in lightning bolts or inside the sun. And there are very good reasons to do this. So like if you look at the properties of those materials, very extreme plasma, they are so different from the three other states that it's often a good idea to just give them their own name and to give them their own category. So that's one very kind of popular way of extending the three states to four. But then on the other side, you have the other tendency and to say, well, it might be a good idea to reduce the number of states that we think about. So for instance, I already kind of mentioned this when I talked about the coffee cup and the hurricane. There is a long tradition now, like several centuries old, of people who say, well, the liquids and the gas, they share a lot of common properties, which is, modifying their shape. And so they call them fluids and they study them together. And so a lot of very interesting stuff came out of this point of view, which kind of make comparisons between the types of pattern, waves and splashes and stuff like that you can get in liquid and the type of pattern that you can get in gas. So in this view, you have solid on one side that can not change their shape nor their volume. And then you have fluids on the other side who can change their shape and sometimes also their volume. But then you have weird stuff. And those weird stuff are not really at the boundary between liquid and gas. They are the boundary between solid and liquid or solid and fluid, if you want to put gas and liquid in the same category. So here is an example of something that you might have already seen on the internet, which is the results of putting water and cornstarch together. You mix them and you put them on a microphone, on a speakerphone, and you look at what's going on. So basically the speakerphone makes vibration like this. And the stuff, I mean, I cannot say really liquid or solid, the stuff, the goo that you've created with the water and cornstarch makes those things. And I mean, I personally like very much those films because they are fascinating, and they are fascinating because they really challenge what we mean by a liquid and by a solid. They challenge the boundary that we had in mind. And really, the whole question of are cats liquid basically sits on the same boundary. It's the same boundary that question what a solid is and what a liquid is. And so basically, I need to remind you now the definition, which I said earlier, which is that a liquid is a material that will adapt its shape to its container. So here you have some experiments on cats where obviously those cats seem to be able to adapt their shape to their container. So it's typically by collecting a lot of those images online and by putting them into kind of a modern scientific language that I got the Ig Nobel, because I use this as a way to ask the question, what is a liquid and what is a solid? So a liquid maintains its shape, maintains its volume, sorry, but it adapts its shape. The important when you look at a sentence like this, and it's amazing that people only really realized this a couple of centuries ago, is that they are words. I mean, to maintain your volume or to adapt your shape is an action. And so as an action, it's something that unfolds during some time. And so it might take some time for you to adapt your shape. So when I pour the water into the glass, the water doesn't immediately adapt to the shape of the glass. It takes some time. And so really, when you realize this, you realize that the question is not really, is something liquid? So the question is not, is a cat liquid? The question is, how long does it take for a cat, or any other material for that matter, to adapt its shape to its container? And so really the question is not really a yes or no. It's not like, yes, it is a cat, no, yes, it is a liquid, or no, it is not a liquid. The question is a number. It's how long does it take for this particular thing, for this particular cat, for instance, to adapt its shape and to become sort of liquid. And so the time that materials take to adapt their shape to their container, the technical term is called the relaxation time. I mean, it's not a joke. It could not have been chosen better, but it's called the relaxation time. And so what rheologists are really focusing on is not really saying if something is liquid or solid, is measuring what is the relaxation time of a material and what does this relaxation time depends on. So for instance, on this image, you have two cats. And imagine that those two cats, they were put in their container, which is their cage here. They were put there at the same time. And so basically, the one on the left apparently had enough time to get liquid or liquefy or relax, whereas the one on the right is still very stiff and very rigid or very solid. And so what people would say then is that the cat number 107, it's not necessarily that it's more liquid, is that it has a shorter relaxation time. And so since we've looked at it after a time that was greater than the relaxation time, it had time to relax, and so it had time to liquefy, if you want. But if we were to leave enough time for number 115, we would also see him relax. So really, rheology, in its kind of emphasis on the importance of time in defining what the states of matter are, they are kind of in line with the Heraclitus, which give them their motto, everything flows, which is that really it's not that those different categories are completely separate. It's not that you have solid on one side and liquid on another and gas separate. Is that you have kind of a continuum of material that can go from one state to another, depending on how long you let them. So the thing is that sometimes you have to wait for a very long time. And so the relaxation time of a material, for a cat, it might be a few minutes. For, honey or some other material like this, it might take a few seconds. But some materials have a relaxation time that can be years, months, even centuries. So on this picture, you have a glacier, which is seen from the top, and a glacier is typically solid. I mean, it's something that you can walk on. And if you can walk on it, it's typically something that you would associate to a solid. But if you wait and if you take pictures of this glacier over months, over years, you would clearly see that the ice, the solid ice, I mean, what appeared to be solid ice, is really flowing down the valley. And so, taken as a whole, the glacier itself is a fluid or is a liquid. But the relaxation time of the glacier is so big that on the timescales that you would normally experience, you don't see this kind of fluid behavior. One great example of this, the fact that it can take a lot of time for a material to reveal its kind of fluid properties, is what you see here. So what you see here is tar. So tar is the stuff that you put on roads. And as you know, when it's warm, it's liquid. I mean, it's really liquid in the sense that like it's liquid on the timescales that you can see. And so the people that work on the roads, that can pour it on the road, and they can place it wherever they want. And so what people did over 100 years ago was to put this hot tar into the funnel that you see here. And the funnel was closed. It has something that prevented the tar from falling out. And so then they let this tar progressively cool down to such a temperature, basically to 20 degrees, something like this, ambient temperature, where it's solid. I mean, it's as solid as the road that you walk on or that the cars use. But then what they did is that they cut open the funnel when everything looks solid, and then they just waited and they waited and they waited, because basically very, very, very slowly the tar went down the funnel, and every 10 years, here you see that you have a drop that is kind of falling. Every 10 year, you have a drop that falls down the beaker. So here you couldn't tell if it's a very like slow material with a very high relaxation time, or if it's just someone who took a picture of like some, water with a black dye. But here I have a time lapse. Sorry, the definition is very bad, but it's a time lapse that shows one of the drop falling. So you see that the drop kind of goes down and then fall and breaks. But what you have to look at here is the clock on the right. So you see that every time, like it took many, many days for the drop to do something that if you were doing it with water would only take like a fraction of a second. So I like very much this experiment because it kind of summarized this idea, the importance of time in figuring out if something is solid and liquid. So how basically rheologists over a century made us switch the question that we were asking from not are cats liquid or is this material liquid or solid to what is the relaxation time, and then to try to measure the relaxation time and try to understand where does it come from. And so I think that with this, I will stop.
Sorry, the Dr. Bilal's screen is frozen. He's trying to.
Okay,
All right, one moment, please.
sure. Thank you, Ahmad.
So Dr. Bilal is restarting his application now. He will be back soon.
Thank you.
In the meantime, and until the doctor rejoins, Zain Al Khalil will be conveying the questions for you, Professor Mark. Zaina, you can start, please.
Yes, hi, Muhammad. How do I check the questions?
I can see the question.
Oh, you can see the questions?
Yeah. So someone, for instance, asked if I expected to win the Ig Nobel Prize. So no, I did not. I wrote, I was a postdoc then when I wrote a paper which was not Are Cats Liquid, but on the rheology of cats. So now you see that it's basically the same thing, but in scientific terms. And I wrote this little paper kind of because I didn't want to write what I was supposed to do. I mean, basically didn't want to do what I was supposed to do, like the serious stuff. So I wanted to have a little bit of fun. So I wrote this and then it was published. And then it's only several years later that it got like the attention of the people who gave the Ig Nobel Prize. So then they reach out and they asked me if I would accept the prize. And so when they did, I was really surprised. And but it was a very good day. I mean, I remember that they had a very kind of they tell someone to tell you that you got the prize and to ask you if you want to accept the prize. But then you have to keep it a secret because they tell you like in the spring or something, and then they announce the prize in September. And so from the spring to September, you're not supposed to say to anyone that you got the prize. And so it was nice. It was a nice surprise.
Thank you. Are there any other questions in the Q&A?
I see.
Guys, if you have questions, just write them down in the Q&A, please. And Dr. Bilal has rejoined.
So I don't know what happened with my computer. Fortunately, my graduate student was around. So right now, my name is Elisa Shayib.
Okay, Eli.
Okay. Thank you, Elisa. Elisa is here. So I don't know how many questions you guys have already answered.
I think we've answered I've answered one question about if I expected to win the Ig Nobel or not, and if I was surprised, and I said I did not expect it, and I was very surprised.
So I have a question. I don't know if anybody has asked it, but if we are in a tall building, 10 floor, 12 floor, 15 floor, and a cat falls, what happens to the cat? And if we turn the cat around, why does it always fall on its feet?
Why does it always fall
Why
on its
nothing
feet?
happens to that cat?
I think, well, I think that back then, so when I wrote the article in 2013 or something like this, in the perspective of the article, so you know that in like scientific articles, there's always like, okay, there's something I need to say, and I want to get this idea across, and then eventually at the end, there are stuff that you put so that like you show that you think about other stuff, and so or you want to cite things that people have done on kind of this rough area. And so at the end of the paper, I think that I mentioned that it would be interesting to see if there was a connection between the rheology of cats and the question that you're just asking, the fact that they kind of always land on their feet. And I think that people have addressed this question, like in the scientific journals, like they've that there is a paper, but I think it came before the paper I wrote on toast. Also, the fact that the toast always fall on the wrong side, and the cats and everything. And I think that there was something, but I forgot what was their conclusion. But yeah, I mean everything is connected.
I don't know if I am able to see on Elisa's computers the questions but we made her a panelist, so supposedly I am able to see. So any ideas about okay, so this question is from Lynn Hijazi. She is biology student. You mentioned relaxation time. My question is what must be taken into account primarily while accounting for this relaxation time? Is age an important factor for cats' relaxation time?
Well, good question. So what I've described was the kind of shift from asking the question, is something liquid or solid, to asking the question, what is the relaxation time, to then I just said that it's the good next step, but I didn't say much about it. Is once you say what is the relaxation time, then you want to know what does the relaxation time depends on. Does it depend on the breed of the cat? Does it depend on the age of the cat? Does it depend on, so all of the questions that you could ask for cats are kind of mirroring the question that people would ask for other types of weird materials. So like if you think of mud, for instance, or ketchup, or if you think of like this mixture of water and cornstarch that I was showing bouncing around on the speakerphone, the people ask themselves this question. They ask themselves, okay, is, for instance, the time, the temperature important? I mean, that's one of the first questions usually is, what is the impact of temperature? So if I change the temperature, for instance, for a cat, it's very clear that the relaxation time depends on temperature. So if it's very cold, cats kind of stay solid. If it's warmer, they get relaxed more easily. And so it's the same type of question you could ask for a kind of rheological material, like more standard. The same apply to cats. And the question are there. The answer, I don't know. I mean, for temperature, it seems pretty obvious. But for age, I would say that the younger cats are usually more bouncing and solid, and the older, more liquid, relaxed.
Elisa, next to me here, she has a question.
Hello.
Hey,
I'd like to ask you, do cats have bones?
bones?
Bones.
Sure, yeah. Like like most animals. But yeah, I mean the question then that you're asking is, how can they be liquid if they have bones?
Yeah, exactly.
Well,
Do they break?
the thing is that it's a question of scale, right? So if you have something can be fluid on some kind of length scale, but not fluid on another. So even it's even true for water. I mean, if you think of water, water is kind of the definition of a liquid. I mean, liquid water. I mean, like water. But of course, I mean, if you were to look inside, like they're not made from bones. the liquid water is not made from bones, but it's definitely made of very hard stuff, like stuff that are much harder than bones, like the kind of atoms and stuff. The rigidity of those atoms is like much higher than the rigidity of bones. So the thing is that it's kind of, you can be made of various things that have different types of rigidity or elasticity, and you can be fluid as a whole, but rigid in some part of who you are.
Thank you.
Thank you. So I have other questions here. This question is from Lina Hajjadiab. From other people who won Nobel Prizes, would you like to meet, if any, if you have anyone in mind, whom do you have in mind to meet from Nobel Prize winners?
Nobel Prize or Ig Nobel Prize winner?
we can go for the second one.
Because Ig Nobel Prize winner, I've met a lot.
No, she meant Nobel Prize winners, because
Nobel
Nobel Prize
Prize
winners, they hand in the...
Yes. So I met a few. I don't know. I never asked myself this question, who I would like to meet as a Nobel Prize. I mean, all of the Nobel Prize that I really like, like that are kind of like my heroes when I was a younger scientist. They're all dead. They're people from like an older generation.
Well, you're very young. This question is from Selina Boujaudi. She's biology majoring student here at AUB. We have a saying in Lebanon, we say a cat has 9 lives, that it doesn't die. How do you explain this commonly used sentence?
Yeah, I don't know why. I mean, it's
Do you have it in France? Do you have the saying in France?
I think we have 9 or 7. I don't remember if it's 9 or 7. Yeah, but we say
I think it's a 7, not 9.
yeah,
Selina, it's a 7, not 9. Yeah, you're right.
But maybe, and yeah, I don't know why people say this. It's not something. The cat falling on their leg is something that I kind of thought about in connection with the rheology. The Schrödinger cat, the dead or alive, is also something that comes back regularly. The 7 lives or 9 lives, I've not thought about, but one thing that what it makes me think of is, I mean, what's kind of magical about this 7 lives or 9 lives is that a life is always supposed to be one, right? So it's a one thing, and so it's kind of radical to think of something that could have several, but I think it interests me for the same reason that I got interested for this cat thing, which is that really it's the first slide of the presentation, is that really when you start digging in question like, is a cat liquid, or what is a liquid, what you realize really is that it's really a question of time. You're not really asking something necessarily just about what the object is, but about your relationship to it, how long you're going to look at it, and so that I kind of like that.
Thank you. This question is from Lin Hijazi. Could the type of container be a factor? Does, for example, the stress on the container affect the extent to which the cat would fit into that container? Good questions.
Yeah. So yeah, I mean, the if the container is your lap, I mean, the knees of like someone that the cat likes, and it's very comfortable on it, and it has its favorite blanket and all of that, well, it's gonna probably relax much faster than if the container is like a cage, like in the example that I gave. So I think that in the example of cats, and in the example of other kind of materials at the boundary between solid and liquid, it is true. I mean, the type of container might have an impact. And the thing is that in the history of rheology and fluid dynamics, this has been like a question from the start. So for instance, even with water, the people like at the end of the 19th century who were studying flows in pipes and stuff like that, they were really concerned about whether or not liquid were slipping at the boundary, and how could you modify the boundary itself, so how the container could be roughened or anything like this. to modify the slippage. And so this was already present at the end of the 19th century, and there are still like a lot of research on those areas.
Thank you. This question is from Hamad Kabakibi. Do you believe that cats adapted to a certain situation while evolving, and for them to maintain their homeostasis, they become classified as liquids?
So, I mean, cats, I had a discussion recently with not an Ig Nobel laureate, I don't think so, but she's part of the Ig Nobel family, and it was Jean, and we were talking about this. We were talking about like, is the cat, like, how much does the cat adapt itself to us, and how much did we adapt ourselves to the cat? And I think that one point that was made was that, I mean, of course, there is fluidity in both directions, but I think one point that was made was that cats were very good at making us do what they want. Like that they had acquired, I don't know if it was because they're so fluid, but they certainly are very, very good at it.
Thank you. This question is from Perla Shami. She is a biology majoring student. Are cats the only liquids that are alive?
Well, there is a whole field that started a couple of decades ago, a few decades ago, that is called active fluids, active matter. And people in this field study cells. I mean, I'm part of this field, at least, I mean, recently. They study cells, they study tissues, human tissues, animal tissues. So they study how a cell can move over a few hours, how a tissue can move. So for instance, there are experiments that have been done in many labs, including the one I'm in, is that you have a monolayer, so you have a tissue made of cells that are connected to one another, but they're only one layer, and then you scratch it, so you make a hole in it, and you look at how long it takes for the close to fill, I mean, for the cells to close the gap, and it takes a couple of days. And when you look at movies like this, I mean, it looks like a fluid. And so people are interested in all sorts of things connected to living materials. So everything that has to do with cells, tissues, or the content of those materials. They said that these are active fluids. And the distinction between an active fluid and a passive fluid is that an active fluid generates its own motion. Like a car is an active thing. But a stone is not. And so in the same way, a cat is active in the sense that it generates its own energy. I mean, of course, if you think bigger picture, it only generates its energy because it gets the food that it needs. If it doesn't get the food that it needs, it's very quickly becomes passive.
Two more questions, if you don't mind. Soline Kyorkian, she's nursing student here at AUB. She's asking, why cats? What got you interested in studying cats?
I won't answer this question. The answer is obvious.
Good one. So last question. This is coming from Lin Hijazi again. I read that the flow rate, which is a usual dimensional control parameter, but considering cats to be active materials, how difficult would that be to measure it in our study, Are Cats Liquid?
So, I mean, I didn't do any experiment on cats. I only took pictures on the internet. I didn't want to get into any trouble. So if I were to ask more involved rheology question and I needed to probe, I would choose probably a different model system. So I would choose a different system than cats. But yeah, I mean, the question also highlight the fact that really the control parameter in rheology, so the relaxation time is kind of the property of the material. And so you take a material, it has a relaxation time, and it's kind of it's kind of bringing it with it. But then you have something that you can do to the material, and this is your control parameter. And the control parameter usually in rheology is either deformation. So you say, okay, I'm taking a material like this and I'm deforming it like this, or I'm twisting it like this, or it's the deformation rate, which is the one that was mentioned by the question. And so the deformation rate is basically the speed or the deformation speed at which you're tearing or twisting something. And the thing is that, of course, like what you're going to be able to observe as a response from of a material, be it a cat or something else, will actually depend on the deformation rate. So if some materials for small deformation rates, they will behave more liquid or more solid. You have both cases are possible. And then the behavior might change when you change the shear rate. So for cats, I'm pretty sure that, I mean, if you start shearing them or deforming them too much, they're not going to like it. I don't know what it means in terms of liquid or solid, but I don't want to figure it out.
Well, thank you very much. I think I am gonna, the best way to conclude this talk is to read the comment coming from Lina Hajjadiab, who's a nutrition majoring student. She's saying, thanks for this entertaining talk. After this talk, cats are actually liquid. As you said, it adapts its shape to fit a container. Only people who have cats can relate.
Okay, thank you.
Good comment, Lina. On behalf of all attendees, I want to thank you for this beautiful and fun talk. I apologize for the IT problem I have, but we saved it with the help of Zena and Elisa. And thank you all for being here. And I want to thank you very much, Dr. Fardin, for your time and for making it. We originally planned for this talk to be on campus. We booked your flight, we booked your hotel, and then we canceled it. It was supposed to happen in January 2020, as far as I recall. But anyway, I hope I will have the chance to host you here in Beirut.
Me too.
Our beautiful AUB campus. But until then, so long. And thank you all for being here. Thank you, Dr. Fardin.
Thank you a lot for the invitation.
Have a good evening. Bye-bye.
Bye-bye.